First of all, welcome, Jonny, and thanks for taking your time and joining us as IES Fellow. Yeah, I just want to make sure, mention very briefly how this fellowship application and meeting happened. We started our collaboration with Scania around 6 years ago. And first thing we noticed was level of novelty and cutting edge technology that these guys are working on. And as part of our collaboration, we got to know Jonny, and he's leading, probably he will give a bit of introduction about himself, but he's leading electrification efforts at Scania. And as you will see from presentations, I had the chance to have a quick look before. So the level of challenges that they're facing to electrify, especially medium to heavy duty the transportation is huge. And I suppose we are very lucky to be here to see their challenges and a bit of introduction about what they do there. And hopefully this will open avenue for further collaboration. So now, yeah, I just want to hand it over to Jonny.
Thank you very much, Mehdi. And I can directly say that thank you very much for having me here as a research fellow. And Mehdi, you've been a wonderful host this whole, well, the week I've been, and we've been everywhere, almost all UK, I think. We've been seeing, including Loughborough, and your university is also a fantastic place. I'm really impressed and almost overwhelmed by everything you're doing here. So I really appreciate being here, and I look forward to the remaining days as well. And with that, yes, as Mehdi said, I'm Jonny Hansen. I work at Scania at the electrification development. So we are making Scania trucks to be propelled of with electric power instead of internal combustion engines. Or we have that part as well, but my focus area is electric vehicle technology. And I have been at Scania. Actually, I've been at Scania for 17 years in total, but I haven't always been working on electric vehicles, as you can imagine. But my journey there is quite far or long. I've been working. I finished my PhD in 2021 at Luleå University of Technology in tribology, or elasto-hydrodynamic lubrication, that we'll be talking a little bit about. And then I've been part of the electrification journey at Scania since then, 2021. So it's a few years now. This talk will be about electric vehicle tribology and technologies. We will cover more or less almost everything. We start with the fundamentals. Where should I look? Yeah, there, I can look here as well. We start with the fundamentals. We will just be very briefly about what is tribology. I think most of you here know all about that. We'll talk a little bit about elasto-hydrodynamic lubrication, which is kind of my core area. And then we will go into what happens when you apply an electric field to an elasto-hydrodynamic contact, and why that is important. We will see that it's very important to know about the transition between elasto-hydrodynamic lubrication or full film lubrication and mixed lubrication in bearing contacts when you have a electric propelled vehicle or electric machine. And what else? Yeah, then we'll look a little bit into how and when discharges occurs in ball bearing contacts, and of course it's connected to the lubricant film and other factors. And then we proceed with electric vehicles. We look into actual stray currents in EVs. We will look into how the damages looks like and some mitigation strategies, and then discuss a little bit the future prospects of research, and then we conclude. All right, so part one, tribology. What is it? As I said, I think this is common for all of you. Tribology is everywhere. In the essence, it's about friction, lubrication, and wear. Here we are not going to talk about all of this, but we're going to talk about the branch called classical tribology, which is where we will find electric vehicles. Now, in a typical classical tribology context, you will have two types of contacts. So one conformal contact and one type which is called non-conformal contact. So a conformal contact will give rise to small or relatively low pressures, megapascal pressures. This can be in piston cylinder liners or this type of contacts. That's not what we're going to talk about today. Today we're going to talk about the non-conformal contacts, which is a relatively small contact point, and then it gives rise to high pressures, so gigapascal pressures, and that leads us to a typical or a special case of lubrication known as elasto-hydrodynamic lubrication. Okay, so what is EHL then? Well, if we look at the ball bearing ball against a raceway, or it could be a gear contact or anything with that non-conformal contact, you have a lubricant and you have entrainment, so both bodies are rotating. Then the lubricant will get entrained into the contact. The viscosity will increase several orders of magnitude, and you will form a lubricating film that will carry the load. This film is very, very thin. It's like comparing the grass on a football pitch to the length. So you, of course, on this scale that we are living in, you can't really see the film. So you need to zoom in. So if we take a closer look on this, if we magnify this contact a lot, then we exaggerate the height scale, we will see something like this. So the dashed curve is the undeformed rolling element or ball bearing could be. And then this black solid line is the film shape. So it will have a very characteristic film shape with a central region and then a minimum film thickness or constriction region at the contact outlet. And then you can see the difference between the dry Hertzian contact solution and the hydro or elasto-hydrodynamic pressure in the red curves there. So it's pretty similar, but you have this very characteristic pressure spike. So this is essentially the elasto-hydrodynamic contact, and this is what's happening in for instance, a ball bearing contact. If you measure this with an optical profilometer, not a profilometer, but like an MTM, or I use a WAM, so a ball on disc machine with interferometry. Then you can actually measure the film thickness, and it will look something like that. So you can see a central region and this minimum film thickness or horseshoe-shaped constriction with the side lobes where the minimum film thickness is. And then, of course, I have to mention the Strebeck curve. When this film thickness that we're talking about, it depends on, for instance, lubricant speed or lubricant viscosity or the surface speed and load. So if you have higher speed, for instance, you will generate more hydrodynamic lift, and at some point, if you have a lot of contact, you have low speed, you have high friction, but then when you have more speed, you generate the hydrodynamic pressure, and then you get elasto-hydrodynamic lift off. So you go through the mixed lubrication regime and into the full field lubrication regime. So you can think that to the left of this curve, you have a lot of wear and stuff going on and high friction, and to the right, you have a lot of low wear and low friction. So that's you want to be somewhere to the right here when you design a tribological contact. Now, for those of you who are a little bit observant, you see that I call this parameter, normally you call it lambda, I call it lambda star, and it's because it's a bit of a revised film parameters. Normally you look or you consider the film thickness, the minimum film thickness over the composite surface roughness. That's the Tallian lambda model, the typical way of assessing or plotting a Strebeck curve like this. Yeah, we will see here in the presentation that method is not really sufficient to find or to estimate where this transition between mixed and full film lubrication is. So I will come back to that a little bit, but the principle is the same. Now, if you for instance would include another dimension here, for instance the influence of sliding, then we can create a map like this. So we have now we have the same thing. where is the mouse? There. I guess, yeah, you see. So here you have the friction coefficient again, and here you have the entrainment speed, and you have the slight roll ratio here. So if you fix the slight roll ratio and you go you reduce the entrainment speed, you essentially create a Strebeck curve, as I just showed you. So this is just multiples of Strebeck curves to create a plane or a map. And then you can see, why are we doing this? Well, because then we get a really good system overview of the lubricant properties. You can identify the rheological regimes and also see where the transition to mixed lubrication is. So here I've also measured the contact resistance to create, that's what you see in the color scale there. So yellow means full film lubrication, and everything that's not yellow, greenish or blue means mixed lubrication. So here we have full film, here we have mixed lubrication. So that's pretty useful. What's interesting is that you can see that normally, if you just look in the Strebeck curve, you can see that, you want to have as high speed as possible to go over the transition to full film lubrication. But here you can also see that there's a strong effect of slight roll ratio. So that's important, especially for gear contacts. All right, so now you know how a lubricant film develops in a ball bearing. And then what if we apply an electric field, and then maybe we can call it e-tribology or electric tribology. So we can look at the Strebeck curve again. We apply a voltage, and then you will create this this contact resistance curve. So the blue curve there, it's essentially how I created the map or the color scale on the previous in the Strebeck map. And then the problem is, I think, there. So then, of course, when you have film rupture or you have metallic contact, there will be electric flow passing through the contact. So not really so harmful, but the moment you have full film lubrication, you can create a spark, because now you have actually created a capacitive contact, and when the voltage exceeds a certain voltage, there will be a spark, and this creates a lot of problems that we will look into later too. So I just wanted to show you this. This is kind of showing you the same thing, but in another way. So now we have this curve here is the lubricant film thickness. If we can control it with viscosity or lambda star, as we saw before. So higher lambda star means thicker film. And then you see the different, here we have boundary lubrication, a lot of contact, and here we have mixed lubrication or onset of EHL, full film lubrication. Now, when you design a contact, as I said, you don't want to have too thick film, because then you have too high viscosity, and that will impose a lot of churning and pumping losses. So there is an optimum that you want to keep this low. You want to be close to this transition between to mixed lubrication. You don't want to be here, because then you have a lot of surface distress as well. Now, the new problem here is that when you include electricity, there is a sort of a optimum or reversed optimum, where this dashed line here shows you the number of discharges, electrical arc discharges or sparks. And you can see that if the film is, if the film is in mixed lubrication, there can't build up a voltage, because you have electric contact. But when there is elasto-hydrodynamic liftoff, you build up a voltage, and you get this. If you think about the voltage, this, for instance, constant 5 volts, and you vary the film thickness, then you can see that you get this curve, and then there is a reverse optimum or somewhere that you don't want to be. And then if you get a even higher film thickness or thicker film, the number of discharges will go down again. So what this means in more clear or directly, it means that tribologists like me are now facing problems in conditions that previously was considered at least relatively safe. So now, as I said, you don't want to have too high viscosity, and you don't want to have too low. So you optimize for this region, but now that's actually the worst place to be. So that's pretty problematic. And that, of course, means that we have to be able to estimate where this transition between full film lubrication and mixed lubrication is. We can do that, or normally, or since the 1960s, we have been using the lambda parameter, the Tallian's model, which is very good for some applications, but not really for this purpose. And so then you might ask yourself, what is wrong with lambda? And the problem is that the transition between EHL and mixed lubrication, it can occur for lambdas much smaller than 3. I don't know how familiar you guys are with lambda, but normally you'd say that lambda equals to 3 means that you're on anything above 3 means that you have full film lubrication. But this doesn't really apply, and especially not for a run-in contact, which most contacts in service are. So I will try to explain a little bit how why I came to that conclusion. So if you run a typical running-in curve, so this would be the friction curve. If you take a brand new surface and you run it in under constant conditions, so you see the conditions here, then you will get this typical running-in curve where you go from something like a relatively high friction coefficient to something very, very stable. In this case, the lambda was 0.5, meaning boundary lubrication. So the boundaries are, below 1 means boundary lubrication, and between 1 and 3 you have mixed lubrication. So quite severe conditions. Now we run this test, and we measured exactly the same surface after test. So 60,000 contact cycles. We can look at the surface, and what you can see is that, first of all, you see it's actually the same surface. It has been a little bit more, the asperities has become a little bit less. It's less red here compared to there, for instance, but more or less it looks pretty much the same. And if we compute the lambda, it's 0.6. Now, since we have measured the contact resistance, we know that this has been. So what's happening in running in is that the surfaces gradually improves their film forming ability, and in the end of the test you get the elasto-hydrodynamic liftoff. So we know in the end of the test that this surface is under full film lubrication, and this is not. So this parameter, or this value, should be 3 if the theory is correct. And clearly it's quite far from 3. And I've done a lot of these tests and seen the same thing, and it's always gets the same. If you run in the surface even harder, you can get full film lubrication at lambda 0.1 or whatever. Essentially, you can do this as long as the surface doesn't seize or scuff. So yeah. And the question is maybe why is this occurring? So we can take a look at these two areas in more detail. And what you then can see, so these are the two small enlarged areas then. So you can compare this number 1, labeled number 1 asperity, to this one. So this is after test in EHL or full film lubrication, and this is before. You can see that if we look in the vertical direction, so this will be vertical in this picture. So the rolling or sliding is directed upwards. So here it's directed to the right. You can see that it has been squashed down. There has been some plastic flow both forward and backwards. You can see the same thing if you look in the horizontal one. So you can see that it has flown both forward and backwards. So this means that it's like standing on a pile of dirt. You get this omnidirectional plastic flow. So it's nothing strange really. It's kind of what you expect. And the other important observation is that if you look in the valley here, so this blue part is a deep valley, and here you have an asperity. So if you look at that here, this is the same asperity than the profile, but you can see that in the valley, essentially nothing has happened. No material has changed whatsoever. So what does this mean? As I said, we see that asperity peaks are only moderately flattened during running in, and we see that deep valleys are hardly affected at all. And when you think about how the SQ parameter, or the surface RMS parameter, is derived in the lambda star, or in the lambda, sorry. Well, you consider valleys as important as peaks, but of course you can't do that, or I mean that's why you don't get any response to the lambda parameter. So that's not a very good way of doing it. The other thing that you might not have realized, or maybe you did, is that when you get this omnidirectional plastic flow, you also increase the asperity radius a lot. So I'll try to show you that schematically. So here we have consider these asperities against a flat surface, and we can look at one of the asperities, and then we put it into contact, and we get this omnidirectional plastic flow. And then if we fit a radii to the post-test asperity the pre-test asperity, and then the post-test asperity, you will see that or you realize directly that the radius is much bigger for the post-test asperity. And why is this important then? Well, it's important because for the same reason as you can create a elasto-hydrodynamic film, you can also create a micro-elasto-hydrodynamic film. The elasto-hydrodynamic film of a ball bearing is largely dependent on the radius of the ball, and the micro-elasto-hydrodynamic is largely dependent on the radius of the asperities. So spikes, the Imperial College group, they showed this very nice paper in the early 2000s where you can see, here you can actually see that they have this model asperities, and you can see that it forms this horseshoe-shaped constrictions on these model asperities. So that is what micro-elastodynamic lubrication is. So what does this mean? Well, it means that roughness, of course, is not rigid. It's deformable in the contact, and that's important to consider. Because it gives rise to this, if we go back to the Seebeck curve, you can see that it gives rise to this intermediate region known as micro-elastodynamic lubrication, and that affects this transition between mixed and full film lubrication. So that's why that is important when we talk about electrical contacts. Another thing that's important here is if you consider these two surfaces, they have essentially exactly the same RMS or SQ parameters, so 0.282, and it's 4 nanometers different, and the standard deviation is very, very small, I can tell you. But you, with your eyes, you can clearly see that there's a huge difference between these two. And the lambda parameter, it can't distinguish between that. But of course, they will have very different film forming ability. Transversal or longitudinal roughness will have side leakage and other ability to form a micro-EHL film. So that's also important, of course, to take into consideration. So all in all, or the key takeaway here is that the SQ is not really a good representation of the asperity height. It doesn't respond to running in changes. Also, asperity radius is very, very sensitive to film formation, so because it promotes micro-EHL. And also, of course, surfaces are three-dimensional in nature, and that affects both micro and micro EHL. And I think, or I know that this is only the tip of the iceberg. So the micro EHL contact problem is much more complicated than this, but I think these are the fundamental pillars if you want to make a new or updated film parameter. And that's what I've been doing in my PhD project. And I will not go through the details here, but you can read about that in this paper. I can just sweep through it a little bit quickly, and then the principle is very much the same. It's the minimum film thickness over the surface roughness, but now it's the deformed micro-EHL surface roughness compared to the rigid body SQ parameter. And what else? Yeah, so we can account for this three-dimensional nature of roughness. So if it's an isotropic or transversal or longitudinal roughness with this, we call it the FQ term, which depends on the asperity radius. So the higher the radius, the more micro-EHL contribution you will get, and depending on the roughness structure, you will also get different micro-EHL contribution. So essentially, you just use this chart to read out. You compute your asperity radius, and then you read out the FQ term and put it in here. Very simple. And then, as I said now, the SQ parameter, it doesn't really respond to running in changes. And that's, of course, not so good, since all machine elements run in very quickly. That's what they do in the beginning. And then I researched a lot of parameter, and I found that this SPK parameter derived from the Abbott and Firestone curve is much more sensitive to running in. It is something like 50 or 100 or 150%, depending on the test, but it responds much more to wear, running in wear. So it's a much better parameter, and actually it's good for several reasons, which I do not mention now since it's a little bit limited time, but it's a really good parameter. And it's actually amazing that it was introduced, I think, in the 1930s, and yeah, they should really get credit for what they did there, and we should be using it more than we do, I think. Then you use the Hamrock and Dawson equations, for instance, to compute the film thicknesses, or whatever way you want to compute the film thickness that you like. So also straightforward, anybody can do that. We did some validation to this, and essentially what you can look at is that we want the blue curves to hit this 100% line. It's the running in test I showed you. It's measured before running in a brand new surface is red, and blue means after the completion of full film lubrication. And then comparing lambda star and lambda. And you can see in all the cases that original lambda, it doesn't really respond to running in because, because of the reasons I mentioned with the SQ and then no micro EHL contribution and so on. But we get really good result. We get some errors, but it's kind of reasonable, I think. So we get really good result with this, and we're very happy about that. I just give you a short calculation example how it can be used. So if we fix the operating conditions and we vary the SPK and asperity radius, and we have our transversal roughness lay, and we solve that, we can get something like this. So you have lambda star here on this axis, the Z axis, and then you have the asperity radius essentially, or the ratio between the asperity radius and the ball radius in a ball bearing. And you have the peak parameter. So you see here that you want to have a low, the higher the peak parameter or the lower the radius, the sharper the asperities, the worse it will be for film formation. So you will get into mixed lubrication. This is the transition into full film lubrication. Now, how does this connect to an electrified bearing then? Well, that means that in this region, okay, here you will have wear and plastic deformations and running in and stuff like that, a lot of surface distress. Here you will be in full film lubrication, but somewhere here you will also get a lot of electric arcs if you apply a voltage to the contact. And at some point, if you increase the viscosity even more, for instance, you will be safe, but then you will have a lot of churning and pumping losses. So we can use the lambda star in this way to understand or optimize the contact. That's kind of what I'm trying to say. And I will show you an example of this soon, where I actually did that. So now you guys know about how the film forms in a bearing contact, and we have a tool, we have lambda star to assess the transition between EHL and mixed lubrication. We know that it's important for when electrical discharges occurs. So I just thought that I would also show you how the discharges occur, why they do. So all lubricants will have a breakdown voltage, a required voltage to create a spark. And that will depend on the lubricant film thickness. Probably it's not very linear in reality, but it serves pretty good as an example, I think. So we have lubricant film thickness here, and we have the allowable voltage you can apply as a function of this film thickness. So for instance, if we have a lubricant film thickness of 0.3 micrometers, you can see that as long as we are below 4 volts, it's pretty safe for a mineral oil. We can apply a voltage and then we can go down and nothing will really happen. However, if we have the same film thickness and we apply a voltage over this, then you will get a release of energy. You will get a plasma or a spark or an arc. And if you measure it, you can measure both the voltage and the current going through there, and you will see something like this. And what will happen is that this arc, even if it's on a very small area, it will cause high energy density. So it will actually be high enough energy to locally melt the surfaces under asperities. And if you think about it, you have molten steel and you have oil. What will you do? Yeah, probably you will quench it, and then you will create some other material in there which will affect rolling contact fatigue life. So probably this is a precursor to reduce rolling contact fatigue life. I stole this picture from this reference here, so I think it's a nice way of explaining it. This is also a pretty new, this is from colleagues in Southampton, and they presented this work where they ran a boundary lubricated contact and also saw, and then they apply a voltage to this and saw also quite distinct influence. So what's important here is that so far I mostly talk about electrical arcing, but it seems that even in boundary lubricated or mixed lubricated contacts where you don't have a spark, you just have electricity passing through, you get also you also affect the tribology. So you can see here you have no voltage, and they ran it for, what was it, 320 million cycles, lambda 0.7, and you can see typical pitting marks and a wear track. But then they applied a small voltage to this contact, and they repeated the experiment with new surfaces, and you see a very big effect. So it seems that just passing electricity, even if you don't build up even if it's due to direct electric flow, it probably influences, for instance, the tribochemistry, lubricant additives and stuff like that, and therefore influences fatigue. So that is quite important as well. This is a nice one because it summarizes a lot of that. We can have different type of electrical damages in a bearing. So you can have anything connected to the surface or subsurface. We will look into fluting and frosting in a minute. And then, of course, you can have degradation of the lubricant itself. And I think mostly that's applicable for grease lubricated contacts. I think I would, if I would redraw this, it's a few years ago now, but also adding the tribochemistry or the additive or tribofilm also will be influenced by the electricity. So that's probably an important upcoming research field, I would say. All right, still coming towards the end here, and now we have kind of looked at the basics. So we are through the fundamentals, and now we will take this knowledge. We know about the lubricant film, and we know that it depends. We know that we need to be in full film lubrication to create a spark, and we know that it depends on the lubricant breakdown voltage of any lubricant. So now we will look into an actual electric vehicle and how bearing currents can occur there and what kind of damages it can create. And of course, for you who don't know what the stray or bearing currents are, this is something that hasn't, of course, been you don't get this in an internal combustion engine vehicle. You need to have an electric motor, you need to have electricity as a source, and then you will get these parasitic currents going through the drivetrain and causing a lot of things that you don't like. Now, bearing currents are not new. They have been around for probably since the first electric vehicles that were, at least the first prototypes I could track down to something like the 1830s, which is pretty amazing in itself. But the first papers I could find, at least, were in the early 1900s, 1910, 1920s. Here you actually see a shaft voltage or bearing current. I don't remember. Yeah, shaft currents, which is pretty cool. So they have been around for a long time, and of course, we know stuff about this. I mean, the knowledge is not new, or the topic is not new. But something really distinct happened in the 1980s. You can see that here. I did a Scopus search for shaft voltage or bearing currents, and here this is the 1980s, and then something really drastic happens. And what happens there is that these IGBT inverters were introduced. So this is the inverter is what takes the battery voltage and converts it into AC voltage that you propel the vehicle. And this technology becomes much faster in the 1980s, and that also sparks the problem with electric or bearing currents. So you can really see that in the literature. And then actually right now we are expecting to have this, or introducing these silicon carbide inverters that are even faster and even more aggressive. So I think this problem will just become worse. And as you all know, the number of electric cars and also now heavy vehicles are really increasing. Scania are aiming for 50% vehicle sales by 2030. So yeah, the electric vehicles are just becoming more, and we really need to have control of this topic. That is kind of the key takeaway here. Yes, so just briefly, where does bearing currents come from? They come from the source is the inverter. As I said, the thing that converts battery voltage into AC voltage or current. And in a perfect world, so normally you have these three phases, a three-phase pulse with modulated signal. So the inverter will create three phases like this, and it will be a discrete on-off signal. And in the best of worlds, the combination of these signals, the average of these, would be a flat line. In reality, it's not. It's something very containing something with high amplitude or high gradients. which is a trigger for bearing currents. So this signal, this result signal, is called the common mode voltage or current. And this is a very, very fast switching, high frequency, nasty signal that is the root cause bearing currents. So if you look at a system, a typical electric motor, we have an inverter sitting here, for instance, and then we have a frame, and we have a stator and a rotor, and we have 2 rotor bearings, and maybe we have a shaft connected to a gearbox. So the currents are created, as I said, in the inverter, and then they go into the machine, and there will be 3 types of currents created. So one is called circulating current. It's kind of an inductive driven current. It's very, very nasty. It mirrors exactly the inverter signal, and it's on all the time and trying to erode surfaces. Then in the worst case, you have something called rotor ground currents. It's essentially, the principle is the same, but you're also allowing it into the gearbox, and that's really bad because the gearbox is very expensive. And then you can have what's called EDM currents, electric discharge machining currents, and that's a little bit confusing because they are actually capacitive type of currents. And maybe you know, but electric discharge machining is a machining method that you can use to create a surface. So it's a little bit misleading terminology. If I would rename these, I would call this some kind of inductive driven current and this some kind of capacitive driven current, because that's what it is. And both of these can create EDM damages. But I stick to the nomenclature because it's well established in the literature, so not confuse anybody. Now, as you realize, if we do nothing, we can get a high risk of the discharge damages in the bearing, so we need to do something. I will come back to that. But also a question I typically get is, but we have cars out there. I mean, doesn't it work? And you can kind of understand that from this one. So you have bearing current on this axis, and you have electric machine size or horsepower or power. And then if we segment it into smaller machines, it can be a pump in a building or whatever, a small electric machine in a radio or I don't know. And then you can have typical passenger cars and then heavy vehicles. And what you can see is that for small machines, you don't really have the circulating currents. You have the capacitive type of current. But then with passenger cars, you get some kind of mix. And then for heavy vehicles, you get the circulating currents will dominate. And this is a problem because these are the really aggressive, nasty ones. And if we look back to the publication, Alger publication from 1920s, as I showed you, yes, they knew about bearing currents in the 1920s, but the problem was much, much smaller and much, much different, because then it was like driven by asymmetries in the motor, but now it's driven by the inverter, and the inverter is so fast. So yeah, that means that the problem right now and is much bigger than it has been before, and the problem is becoming much bigger machine you do. So the head we are just about to, or yeah, we are some in, but we are electrifying the heavy vehicle fleet right now, and it's just increasing. So we're kind of in domains where nobody have really been before. Okay, so we have a little bit, few more minutes. Did you say 45 or?
Yeah, 5 to 10 minutes you go.
Okay. So I will show you some actual measurements then from an electric vehicle motor. Yeah, so here you see a typical shaft voltage measurement. Let's see now. So yes, this is operated under constant operating conditions. So 5,000 RPM, the film thickness is constant in the bearings. And then if we measure the shaft voltage, you will see a really nasty signal looking like this. And then what we can do is that we can say that we don't know, but we can say that, okay, potentially a peak that is above 1 volt is potentially harmful. And then we can count those peaks. So in this case, it's 15 discharges or per millisecond. So something like 15,000, I guess, per second. So quite a lot. And then if we do this then for a whole range of RPM, so we vary the film thickness in the bearings essentially. Then we can see if the lambda, and we can compare it to the lambda star parameter. So that's what I did here. So now you have number of EDM events or number of arc discharges in the blue bars, and then you have RPM or speed here. So and then you have the lambda star here. So remember now, anything below 1 means mixed lubrication. So you can see here that here we have mixed lubrication. It's not a lot of discharges going on. But then as the film or the lambda star increases, we go into the full film lubrication regime from mixed lubrication. You get more and more of these discharges. And then it goes down again. So this kind of confirms the hypothesis. You remember that I showed this bell-shaped curve or something. So we kind of see that the behavior here. And now what's important is that every single one of these discharges creates a tiny, tiny little surface damage. And from the beginning, if you look at a bearing raceway, you will see a gray band like this. It's not a tribal film. This is a frosted, electrically frosted, damaged surface. And then with time, if you continue to run this, it will develop these fluting or corrugation marks that you can see here. It looks actually, it looks pretty almost. It looks like you have deliberately done this. It's kind of amazing how it can create this. And then as you realize, these furrows or corrugation marks, they will create a lot of vibrations and noise and increased friction, and of course reduced rolling contact fatigue life bearing. So it's really, really bad. And especially in an electric motor that is very, very, or comparably doesn't have so much size, it's pretty silent. So it's a problem if it occurs. And we can look, here you see more in detail how it can look like. So this is called electric fluting. It's a rotor bearing under different magnification. So this is the outer raceway or rotor bearing. And these are the corrugation marks. We zoom in and see this, and you see this. It's not supposed to be there. It should be just a shiny surface. And then we can look into how, if we look in the height information, we look with an optical profiler, we can see how deep these furrows actually are. And that's what you see here. And then we can look at the profile, so you see it better. Here you can see that it's essentially a perfect sine wave. It's something like peak to valley, I don't know, 2 micrometers or less. It can be much more. I've seen cases where it's been 20 micrometers or so. This is a brand new surface, and this is actually how it should look. Even after some running in and wear, it should pretty much look like this. So you can see that it's a huge difference. It has really changed the surface, the nature of the surface. And then if we look at how a typical lubricant film thickness is, so this is a typical operating range for a lubricant film thickness in a rotor bearing. Then you realize, of course, that the valley zones will cause loss of hydrodynamic pressure, that will cause loss of lubrication. You will get these peak zones will take all the stress or a lot of the stress, and that will of course be a precursor to reduced rolling contact free life. So not so good. And normally here I get the question, but how can you really be sure that this is due to electric discharges? Because you can also create a pattern like this mechanically. If you have vibrations, for instance, and a lot of sliding. And then, so I measure both. So I took a new, here you see a brand new bearing surface for comparison. And this one is the same, it's the rotor bearing raceway. But if we run the machine with a dyno, so no electricity involved, just mechanical rotation, then you can see this classical running in. You get this omnidirectional plastic flow that I talked about before, and you get, that's essentially what you see. You see the main structure remains. And then if we take a new bearing and we connect the inverter and we run it with the inverter and do the same thing, you will see this. So these are typical, you can see these small little craters, and they are typically created by electric discharges. They are roughly, what can it be, 2 micrometers or so in the radius. Okay, we need to mention just briefly, of course, there are things to do. We can mitigate this. And we look at the same picture again, as we already saw. And then, for instance, what we need to do is that we need to implement this low impedance path to save both the bearing, but also the gearbox. And that can be done with different ways. So one way is to have an electric conductive lubricant. It can be an ionic liquid, or it can be other additives as well. I think there are already some manufacturers have tried this, and maybe they have been beneficial, but I think mostly this is a future research topic. I don't think it's very, it's not really on the shelf, any product like this. So what most vehicle manufacturers are doing, that's that they are grounding mechanically with a grounding ring or brush and things like that. And that has been done since probably for 100 years or more. So in that way, you can kind of solve the problem on the drive end side or close to the gearbox. You have a good impedance path, you bypass the bearing, you lead the current away from the bearing. Now you still need to here's just an example how it can look like. This is a grounding ring where you have a PTFE ring which somehow leads electricity. But you still need to solve the problem on the other side, and you cannot really ground it because you have to remove this red circulating current. You don't want to ground it because then you will still let it live. You want to remove it, and the way you do that is by implementing. One way can be to go directly to the source and put the common mode choke, and you will reduce the circulating current. As you can see here, the red curve is original and the blue curve is with a common mode choke. but what most people do is that they use a hybrid bearing or a ceramic bearing or something like that. So that's just the balls are made of ceramic, non-conductive material, and then you block away the circulating current, so you don't let it live anymore. You take it away. So the best way to build an electric motor for a passenger car, for instance, that's to have a well-defined grounded side and a well-defined insulated side, and then you will be pretty safe, I think. All right, final part. 1 more minute, if that's okay. So of course there are some possibilities or prospects ahead. The problem is more or less, I mean, as I said, for small machines, it might not be a big thing, but for bigger machines, even if you have a grounding and stuff like that, it can still be a problem. And you can see that, for instance, this is from a paper or thesis showing how the situation is in the wind turbine industry. So there, still the bearing failures are the leading cause of problems, and many of these damages are because of electricity in the bearing, so bearing current essentially. So that kind of, I mean, and they have been doing this for quite some time, and they still have a lot of challenges. So that kind of shows us the magnitude of the problem. There are of course grounding rings, and many people think that but you can ground the shaft, so there is no problem. But the problem is that if you increase the current or the voltages, then this grounding may not take all the electric load, so that is a challenge in itself. That it's very, very difficult to ground things away. And as I said, I already mentioned the electrically conductive lubricant is pretty interesting, but I think it's not yet commercially available, at least to my knowledge. Also, I also mentioned this a little bit, but how the electricity affects rolling contact heat is not really known. Partly what happens when you create these sparks, and I showed you, okay, there might be some material changes going on and so on. That's one thing that, it's a hypothesis, I would say, but it needs more research. And another thing is, maybe that's what I will say here. So how tribofilms and additives are influenced by the electricity. I mean, all the lubricants are manufactured for ICE driven vehicles. They are not manufactured for having an electricity in there or a voltage. And of course, these are polar additives, so they will respond to the electricity in some way, and that might not be so good, as we saw in the Southampton study as well. And I also mentioned this, that the IGBT, we are going from very fast inverters to even faster inverters, and of course that's expected to make this thing even worse. You can see this if you search in Scopus. You can see that it's very much driven by the inverters, the IGBT inverters and silicon carbide inverters, and I think what am I saying here? There's a lot of focus in this area right now, and I think it will become even more now when the heavy vehicles are entering this stage, electrification stage. It will become even more important to control and understand this bearing current problem. Some final conclusions, a little bit quickly. I'm a little bit over time now, but we have seen that the electricity adds further challenging to an already challenging discipline, the tribology discipline, and damages are now possible in full film lubrication or EHL, which we considered relatively safe before. That is actually the worst case you can be right now if you don't have good control. And we know that we need to be able to estimate where this transition between full film and mixed lubrication is because of this. And the lambda is not really so good, but the lambda star can be used for that. And then we have looked into stray currents in electric vehicles, and we have seen that there are three main types of circulating rotor-ground and EDM currents. We see that the surfaces leads to very nasty sine waves in some case, called fluting, and this influences, of course, energy efficiency, service life, and makes a lot of noise and stuff. There are some major influencing factors that influence the bearing current. One of them are the lubricant film thickness and, of course, the properties of the oil itself, the inverter, the inverter signal, or the common mode voltage and the common mode currents, machine size, and of course your mitigation strategy. There are many challenges and opportunities ahead, and I mentioned some of them. I think the trend is towards more research in this area, and that's pretty good because I think it's a super interesting topic. So with that, I am finally through, and if you have any questions or if you have time for that.
Excellent.
Thank you.